Hello, everybody. Welcome back. Now, if you recall, the starting point of our conversation regarding the concept of limits, you may recall we started by looking at, if you simply recall, the hiking example, right? So while you're hiking, like let's say, you see some kind of a strange behavior at a certain point. Now, this could be a pitfall if you have no idea, and if you directly go and jump, and we know it could be a catastrophe, and we have no clue. So, we wanted to proceed with caution, right? So, that's exactly what we wanted. Now, how can you see this particular behavior, this particular pitfall right here, where the function is not defined? That scenario, how can you visualize it in terms of a computational example? And that's exactly the purpose of this lesson. So in this lesson, we will go over limit computations. Basically, we are not going to play with graphs anymore, and we will be working with expressions, function expressions, and we will do limit computations explicitly in an increasing order of complexity. And while we do that, in each example, we try to explore this particular behavior, this interesting behavior where the function is actually not defined at a given point and it's kind of a mystery. So what does this mystery look like when you consider a computation of limit? Now look at this example number one. If you look at uh, or if you recall what you did in algebra when you're given a function, and if I ask you some kind of a domain value, some value, some x value, what we're going to do is to plug it in the function and see what we're going to get. Now let me do it right away in this example. Now when x goes to 2, if I try to explore this particular scenario directly by plugging in the values, this is how it's going to be. When I plug, now I'm going to write this one in red with a little bit of gap, because eventually I'm going to just erase it in anyways, because it's not really meaningful. But always I will do this as a rule of thumb. When I have a limit computation, I will just plug it right away and see. When I plug it right away, this is what we get. When x equals 2, plug it in the position of the denominator. So that's going to be 2 square minus 3 times 2 plus 2 divided by 2 minus 2. Now, of course, you can see a problem in this computation, right? Once you see 2 minus 2 in the denominator. But that's not, I mean, in algebra, putting a 0 in the denominator is a disaster. But that is not the worst thing that can happen. In this scenario, if you look at the numerator also, the numerator turns out to be 0 as well. So what you're going to get is 0 divided by 0. Now, dividing a number by 0 is bad. That is an enemy in algebra. But dividing a 0 by 0, dividing the 0 by 0 itself is a catastrophe. Now, the whole point is this is not a well determined, this is far away from being determined in mathematics. So, this kind of a scenario is called indeterminate form. So nobody is going to ask you this phrase, indeterminate form. You do not need to really have that particular phrase to graduate from calculus. But whenever you teach this concept to somebody, make sure that you have this particular phrase associated with this pitfalls, right? So indeterminate form, this is one of them. This is one of them. There will be more in upcoming computations. We will see. So one of them is this, and there is something called infinity divided by infinity. It is not determined. And if you have infinity minus infinity or infinity times 0, there are many situations where this meaningless expression can pop up. So whenever we have this, now all of these are just exploring the situation. These are all of these are what ifs, right? So what if I jump right at this function value? What would happen? So this is what would happen. It's going to be a mystery. We have no clue. It's not a mathematically acceptable answer. So in this case, this is what we're going to do. We're not going to do anything except for doing an algebraic trick. So calculus is based on algebra in this way. If you directly plug, you're going to end up getting 0 over 0. Instead of doing that, this is what I'm going to do. I'm going to simplify this first. First of all, I'm going to hold this limit computation until the next step. And I'm going to do a simplification so that I can get rid of a bad factor, which brings both the numerator and the denominator to 0 together. How do I do that? A quadratic. You can factor it. Now, factoring a quadratic, if you have some difficulties in that, I would recommend at this point to go ahead and have that review. You can use the textbook, and I provided the initial review from the textbook, and you can explore it more and go ahead and brush up your algebra skills. Factorization is going to be key in this entire journey. And now look at this. Once you have this, you can get rid of this bad factor, which is x minus 2. Now, if you look at that carefully, think about this x minus 2. When x goes to 2, x minus 2 is the one bringing it to 0, both the numerator and the denominator. Now, when I cancel this, one may counter argue saying, oh, you actually cancelled 0 by 0. You just got rid of that somehow by tricking us. No, that is not what I did. Don't forget the very starting step of limits. I told you, when it comes to limits, we are not looking at the function value at that point. What we do is exploring the function value around that point. So when you consider around, when you consider the proximity, actually x minus 2 is not 0. Therefore, you can cancel it with each other. Therefore, you got rid of this x minus 2. Now you end up getting a simplified expression where you have the luxury of a direct computation. Once you have it, now you can plug in this value. Once you plug in, you're going to get 2 minus 1, and that's your answer. So now, what is the takeaway from this particular example? Now, when you have these kind of examples, like let's say a polynomial divided by a polynomial, and once you plug in, you end up getting 0 over 0. That simply tells us the bad factor. There's a bad factor hidden at the top and at the bottom. So this can be performed whenever you have a rational function, which means when you have a polynomial divided by another polynomial. Let's take a look at another example. Example number 2. Now, since we know where it is heading, let's do this right away. In fact, why don't we do this? Why don't you go ahead and start working with the example and have quick pause to this video and try it out. And then let's see, take a minute or two. And then once you have your write up, then unpause this and see the work. All right, pause it now. All right, I hope you gave it a try. And now let's do it together. Now, the first thing that I'm going to do is, even without saying it or writing it, let's see, I'm going to have this rule of thumb that is none other than plugging in the value x equals to right away at the top and at the bottom. And when I plug it in, do I get really 0 over 0? If I get 0 over 0, that's only when I need to do this meaningful simplification. Otherwise, I already have a meaningful value. So now, when you plug in x equals 2 at the top, you're going to get 4 minus 4, it is 0. And when you plug in 2 at the bottom, you're going to get 4 minus 2 minus 2. So that's going to be again summing up to just 0. So 0 divided by 0. So it is meaningful. It is meaningful, or this is going to be a meaningful limit computation, but Direct computation will not give you a meaningful answer. It is indeterminate. So now this is what we are going to do. Let's do the computation. When x goes to 2, I'm going to hold the computation. Do you see what I'm doing? I write that limit. I just transfer that term, that expression to the next step, and I will hold it until I do enough with this expression and I simplify it enough. So let's simplify. The top is x minus 2 times x plus 2 divided by the bottom is x minus 2 x plus 1. Again, I told you how important the factorization is going to be in this journey. Now, by any chance, if you have any struggles with that, I recommend you to brush it up and review your algebra. If you need further examples, I can help you with that, and get connected with the tutor assigned for this class. And I don't really care how you're going to do it. I mean, whichever the method you prefer, I really want you to be familiar with that kind of a computation. You should be comfortable with this transformation right here. And please address it without delaying it, or procrastinating it. All right. So now, when you just do the simplification, look at this. The bad factor is right in front of you. You can get rid of that once you do that. If you look at this very carefully, in fact, you can do this. You can work with this kind of problem in one single line. You do not need to proceed to a second line. This now, what's remaining here can be computed right away when you plug in x equals 2, because the bad factor is already gone. So when you plug x equals 2 at the top, it's going to be 4 plus 2 plus 2 is going to be 4, divided by, at the bottom, it's going to be 3, and that's the answer. Look at how simple it is. Now, this could go to a different level. There could be different levels of this computation. Now, in this particular scenario, look at this. Oh, this seems a little scary in terms of factorization. Let's see. Let's pause it for a moment. Let's take a pause, quick pause, and try to do it yourself. And then let's revisit. Pause it now and do some work. Spend a couple of minutes on that. All right, I hope you gave it a try. Now, if you try to factorize this right away, it could be difficult, but it's not impossible. But I don't know whether it could be even impossible. I didn't even try that. Do you know the reason? Can you see the reason? This is where I would suggest not to forget rule of thumb. Just plug in the value and see whether it's gonna head towards a meaningful limit computation. Now, if you directly plug in x equals 1 in this expression, this is what you're gonna get. By direct computation, I would call it by plugging in directly without doing anything. Now, when you're plugging in, this is what you're gonna get. You're going to get 3 minus 5 plus 4. Obviously, that is not going to sum up to 0, which is a good sign. And in the denominator, when you plug in, you're going to get 2 minus 1 plus 3. That is not 0 either. So now the top is going to be just 2. The bottom is going to be 4. And that's what we have. Now, this is not 0 over 0. So that simply means you do not need to panic. So even if you have 0 over 0, you do not need to panic. Of course, we know what to do in that occasion. Now, this is a scenario that you can even relax further. And what is really happening here? Now, let's speak graphically, right? So if you look at this scenario graphically, this is how actually it behaves. I do not know how this function, I mean, this is a mystery. I may need to explore it further in detail to understand what's happening in that function. But what's really happening is around 1, when I consider the behavior of this function, I don't know whether it's increasing or decreasing, but it is approaching the height of 1/2 from each end, and the function is well defined at that point. So simple idea is, when you have this kind of a smooth continuation of a function at a given point, when it is not giving a surprise of 0 by 0 or any other indeterminate form, what's really happening is you're playing with a smooth function. It is continuous. And with that, you're going to get a perfectly well-defined number. So this is what I'm going to do once you have a perfectly well-defined number like this. Don't do anything. This is not needed either. What you need to do is just to stay with that value, and that would be your answer. So don't forget the rule of thumb: plug in first, right? Plug in first and check whether it gives you a meaningful limit computation in terms of an indeterminate form. Now, let's look at this scenario. Now, computations can have different, I mean, that can offer you a variety of scenarios. And in this situation, if you look at this computation, now let's plug it in right away and see. First of all, uh, if you do not see this particular expression properly, and try to understand it, read it again, and make sure that you understand it well. It has two fractions, one at the top and one at the bottom. The purpose of this big division line is to separate these two uh, pieces and to give an idea of the order of this computation. So yet you have a numerator and you have a denominator. So now this is what we are trying to do in this computation. Now let's plug it in. Once you plug it in, can you see the top is going to give you 1/3 minus 1/3? It's going to be 0. And the bottom is going to be, of course, x minus 1. When x goes to 1, it's going to be 0. So 0 over 0. Now you confirm that this is heading towards a meaningful limit computation with some more effort. At least we know the direction. It is not like the rule of thumb that we're going to have just a simple plugin and get the value right away. Now, how are we going to deal with this? Again, we recall algebra. We call algebra. Algebra is on our only friend in this scenario. You need to do algebra uh, purposefully. So this is what we are going to do. I'm going to hold the limit computation until we prepare, until we cook this function enough. How are we going to do this? Let's look at the top separately. This top function. You have a fraction minus another fraction. What comes to your mind? What kind of simplification can you see? Take a moment, take a quick pause, and try to do it yourself. The purpose of making some of these pauses and asking, when I ask you to work with some certain examples, even before me, is to show you how obvious some of these computations are, right? So try to look at the numerator and try to simplify it. In algebra, when you have this kind of an expression, what would you do in the next step? Do it. All right. I hope you gave a little try by pausing the video. Now let's see uh, what we should do in this case. All right. So I'm going to take this numerator and let's simplify it. I'm going to take the common denominator of that numerator. So that's going to be x plus 2 times 3. And when I do that, don't forget I need to cross multiply these pieces. And what I'm doing is the common denominator simplification. So 3 comes to the top of this and minus, and then I'm going to bring this x plus 2 term to the other side. So don't forget you have a negative sign here. So you need to have x plus 2 right here. And this piece is nothing other than just the numerator. And the denominator, after this big division line, it still appeared right there, x minus 1. Now let's simplify the top. Can you simplify? The only simplification lies in the numerator. So let's simplify the numerator further. So you're going to get 3 minus x minus 2 divided by, uh, let me write 3 in front. So 3 times x plus 2. So in that way, I can make it neat. And then after that, you divide this term again by x minus 1. Wait a minute. Now you need to simplify this, right? So you have this fraction and you divide it again by this. So where should I put this one if I try to simplify it together? So when you perform a division twice, this is how it happens. X minus 1 will be in the denominator. By any chance, if you do not see this, and this is how it would be. You have something like a over b right there. And then you divide it by just like c, right? Since you do that, I will write it like c. I'm not going to write it just like c. I will write it like c over 1. Because most of you may recall the simplification in this way. When you have this scenario in the denominator, when you have a fraction in the denominator, you can flip and multiply. When you flip and multiply, what you're going to get is a divided by b times 1 divided by c. Now combine a divided by b. Let me just write it over. A by b times 1 over c. Look at how these two denominators are getting along with each other to make a new denominator of b times c. That's exactly what happens here. So all of these are simple algebra stuff. Just in case if you do not recall, that's why I wanted to provide that additional background, but you should recall it. If not, review it. And now with that, this is what we should do. Let's simplify the top. So you're going to get, yet I'm holding this limiting operation. It is to be performed later. And then I'm going to get 1. Look at this. 3 minus 2, it's going to be 1 minus x. The whole thing is divided by 3 times x plus 2 and x minus 1. Now I need to get rid of the bad factor, but I do not quite have it yet. Can you see there is some kind of a mismatch? I do have 1 minus x here. I do have x minus 1 here. They seem kind of related to each other. But now if you do not see it, I again recommend have a quick pause to this video and try to see how that relation is built up. If you do not see it, take a moment. All right, I hope you gave it a try, and this can be written in a different way by factoring a negative sign out of it. That's when you factor out a negative sign, it becomes negative 1 plus x. In other words, x minus 1. It is away from a negative factor. It's not that far away. And once you do that, can you see the cancellation of the bad factor? The bad factor holding us until up to this point is x minus 1, which would bring both the numerator and the denominator to 0 at the same time. Now, once you get rid of that, you can plug x equals 1 in this. And when you do that, the denominator gives you 3 times 1 plus 3, it's 3. And don't forget, in the numerator, of course, you did not, excuse me, you did not cancel the entire term. What you canceled is just only one of the factors. It's still having 1 at the top. And don't forget this negative sign. So it's negative 1 over 9. That is the answer. And you do not need to it is not really necessary to simplify an answer. In most cases, when you use mathematics also for your assignments, it is not going to ask you to simplify to the bottom layer. But my recommendation, when you work with the computation algebra, it's better if you use a little bit of a simplification just to have peace of mind. All right, so now let's try to proceed to one more example, kind of similar, but now it's combining two different aspects. Now I recommend you to have a quick pause at this point and to work on this example before proceeding to the explanation of this particular scenario. All right, take a moment, pause the video recording, and work with this example. All right, I hope you gave it a try and see how it would work. Now let's see, let's verify your work. Or let's try to recognize where you had some difficulties with. So now, to work with this example, again, I'm going to do the same thing. Oh, wait a minute, I forgot something. I should, in fact, you practice the rule of thumb. First of all, is this a really meaningful limit computation that I'm heading towards? Plug this value, x equals -1 at the top and the bottom, and see it for yourself. And when you plug it at the top, you can see, even though there's a fraction, you will end up getting -1 plus 1. It's going to cancel with each other. And at the bottom, it's going to be just -1 complete square, which is going to be +1 divided by +1 minus 1. That would be 0. So you end up getting 0 divided by 0. So it makes sense. Now, what we are going to do in the next step is, after the verification of the indeterminate form, now in the next step, let's try to simplify. Let's try to employ algebra to work with this problem. So what I'm going to do at the top is just a simplification, right? So here, common denominator. When you prepare the common denominator, it's going to be x times 1 plus x. So that's what you have at the top. And at the bottom, you're going to get the factorization. Let me have the factorization. Now, don't forget, when we had the factorization problems right at the beginning without having all of these fractions and everything mixed up together, what we did was like, yes, of course, we wanted to factorize to see the bad factor. So that's exactly what we are doing here. We try to explore the bad factor and try to recognize the bad factor. And now again, use algebra of these fractions. Again, a divided by b, the whole thing is divided by just c. We know all the denominators are getting together to attack this numerator, and it will be just like uh, x times, x is already right there in the denominator, and then these two are getting along with the same denominator, x minus 1, x plus 1. And can you see the cancellation of 1 plus x or x plus 1? 1 plus x, x plus 1 is just the same thing. So that gets cancelled. Now, don't make that mistake. The numerator is not empty. After the cancellation, you end up getting 0 at the top because you cancelled it by a division. So how many copies of x plus 1 you had at the top, that many you should leave it right there. So that's going to be just 1. So 1 divided by, and now plug in this value, x equals -1 here. You're going to get -1 times -1 minus 1. So that's going to be -2. So altogether, that will bring us to 1/2. And that's it. Look how simple it is. You can combine these different scenarios. Now, let's explore another domain of these computations. In this example, we do have another surprise. We have two square roots. Now, when you have these square roots, how are we going to deal with them? Can you just simply get rid of them? Unfortunately, there is no easy way around this. Now, at this point, To have this learning process again, to make it straightforward, at this point, have a quick pause. Let's consider this as a fresh problem and let's try to generate your thought process. When you have this kind of a situation in terms of algebra, how would you proceed? What can you do to simplify this? I do not need you to write down everything, but at least have a quick pause and ponder about it for a couple of minutes. All right. I hope you gave a little bit of a thought. All right. So let's see. In this situation, in this kind of a scenario, this is what we are going to do. Since we do not have a nice way of simplifying this, now don't forget you cannot combine all of these into one single square root or anything, because square root function is not a linear function, so you cannot just bring it together. What you need to do is something indirect. What we're trying to do is to multiply. Now in this case I will just rewrite this expression. Usually I would do it right here, but other than messing up with that expression, the given problem, I will write it separately. I copied it down, and then I'm going to multiply the top and the bottom by a certain term. What is that particular term? That term is none other than, okay, do you recall some kind of a resemblance? It is exactly the numerator, but other than having a minus in between, now I do have a plus. Do you recall what this is called? This particular term is called the conjugate. Conjugate, and it has conjugate of this term, in other words, the conjugate of the numerator of the original function. So this conjugate can offer you an amazing simplification in the next step. What is that simplification? We are going to simplify only the conjugates, the mutual conjugates, but we are not going to simplify anything related to the extra copy that we have in the denominator. So let's try to simplify. Let's try to multiply this. And the simplification, let me do it other than just working out all the information here by following one step at a time. Let me show you what's behind the essentials. It is none other than this fact: a minus b times a plus b. From algebra, you know what happens when you combine these two. You're going to get a cancellation of middle terms where you're going to get minus ba plus ab. Those two will cancel with each other, leaving only two meaningful terms. It's a square minus b square. And at the same time, if you weave this the other way, this is exactly the factorization of uh, difference of two squares, right? But the factorization is not what we're explaining. I mean, it's not what we're trying to explore here. What we're trying to do is just to FOIL, right? Just to combine terms. So when you do this, now let's try to proceed. And that's exactly what you see here. And the purpose of this entire computation is to square these two terms, and this one is acting like just a, this one is just like b, and in that case this entire term is nothing other than a plus b. So you have a minus b times a plus b. It's none other than x plus 1 with the square of this, and then square root of 3 square. So a square minus b square. The whole thing is divided by x minus 2. And don't forget, I told you earlier, I'm not going to touch the denominator, the extra copy that I put in the denominator. You will see the reason in a moment, because that's not getting involved. So when there are terms that are not getting involved, leave them separately, because the computations could be much more easier in that way. Now when x goes to 2, what would happen? In the numerator, you square essentially a square root. They will clash with each other. the square root will cancel the square. So that's going to give us just x plus 1 at the top and minus square root of 3 square. That's none other than minus 3. All right, so x plus 1 minus 3 at the top. And at the bottom, you have just this term. I will just pass the denominator right away. And now look at this. This term, if you really want to wait until the next line, you can wait. You're welcome to wait. Or if you can see exactly what this term is, you can cancel it right away. This entire term is none other than x plus 1 minus 3. It is none other than x minus 2. So x minus 2 is getting cancelled with this x minus 2 right here. But since this is the very first example of this category, let me just do it for you. X minus 2 is now sitting at the top. X minus 2 sitting at the bottom with the other term. Now, you have the cancellation of the bad factor. With that, don't forget at the top you have 1 as a factor. So now you can plug in and you're going to get 1 over, when you plug x equals 2 in this expression, you're going to get 3 root 3 plus root 3. So what essentially we have is 1 over 2 copies of square root of 3. And that's exactly where we are going to just leave the answer as it is. Now, in algebra, when we see a square root in the denominator, we have a special simplification. We called it rationalization of the denominator. You try to get rid of the square root from the denominator. Now, shall we do that? Now, if you keep wondering, oh my goodness, I do not recall what that means, I do not recall that process. Now, hold on for a second. We are not going to worry about that in calculus. The purpose is to have a meaningful value, and once you reach that meaningful number, that's it. We do not need to simplify it to a workable form, just leave it there. So this answer is perfectly well defined, and that's exactly where we're going to leave this answer. So that's the process. Now, the takeaway from this particular problem. Now, if you have, uh, like when you work with these problems, if you came up with some kind of a uh, difficulty at a certain point, understanding a certain problem. Now, that's exactly where you need to have a quick pause or go back in the video, rewind it, and make sure that you go over the given example enough time to digest it well. If not, since these problems are having gradual increment of sophistication or the level of difficulty, just proceed one after the other. Now, if you're comfortable with this computation, the next step is this. Now, let's look at this. Let's proceed to example number 7. And now, my recommendation. Let's have a quick pause and pause this video and work with this by yourself as much as possible. And then wherever you get to, if you get to the final answer, that's perfect. If not, you will recognize where you got stuck, and then the explanation, looking at the explanation, would be much more meaningful. Now, pause the video and start working with it. All right, I hope you gave it a try. Now, in this particular example, I'm trying to combine two different scenarios, or in fact, I have a little bit of a typo, or in fact, if you gave it a try already, my apologies, because I wanted to make it a meaningful computation. Now, the first thing, let me do this. Since I gave this problem in this form. Now, if you proceed with this problem, that's perfectly fine. Can you see this has nothing to offer in terms of beautiful limit computation, because once you plug in, you're going to get this, right? So once you plug in, you're going to get 0 at the top. It's root 4 minus 2, that's going to be 0 at the top, and at the bottom it's going to be 1 plus 1 minus 1, so it's going to be 1. This is the answer. Just plug in. Don't forget the rule of thumb. But in fact, I should admit, I made a mistake when I prepared this example, and apparently I am now realizing it. So let me prepare. Now, first of all, if you got this answer, that's perfect. That means you didn't forget the rule of thumb. Now let me make a meaningful question out of this. Let me just make a copy of this example and I will paste it. I will in fact do it like this. I will paste it. Let's paste it. Let's move it to the top. This is example number 7 where you got it perfectly correct. That simplification. Just let me leave it right there. Oh, all right. So now, all right, if you directly work with example number 7, this is the answer. You got it already. Now, let me do something. Let me prepare a bonus example. A bonus example. Now, let's think about this. What if I had, other than having minus 1 here, right? Here it's minus 1. And what if I make it minus 2? Now, if you plug in x equals 1, in this situation, do you get a meaningful limit computation? Or do you end up getting an indeterminate form? If you come up with an indeterminate form now, again, let's have a quick pause. Let's try to work with this problem. Let's spend a couple of minutes and pause it right now and think about it. All right, I hope you gave it a try, and let's see what we are going to do, what we can do in this scenario. Now, if you plug in x equals 1 right away, you're going to get 0 divided by 0. Now, this becomes a meaningful limit computation. Now, to work with that, this is what I'm going to do. I will plug x equals 1 right away. Okay, so I plugged it in already. So now I'm not going to do that again. Instead, let's do the simplification. Let me do, in fact, the simplification in line number 0. Let me import a different color. Now, this is what I'm going to do. This is line number 0 of the problem. I will immediately multiply what's given with the conjugate. We know the trick. The conjugate simplification is a lifesaver in this kind of a situation. So the conjugate, in fact, has a plus other than having a minus. So x plus 3 and a plus in between and plus 2. Now we know where to perform the simplification and where not to perform the simplification. So do it. Do the simplification and then let's see where we go from that. Now at the top, when you simplify it, what you get is the difference of squares. And when you do that, now you don't need to spend many lines to get there. Once you see it, you just get rid of the square root here. So x plus 3. And then you square this term. Don't forget, it doesn't have a square root. So when you have 2 square, that is 2 square, which is going to be 4. The whole thing is divided by now this term. And that's where this bad factor, the bad factor hidden in, so hiding in, therefore you need to factor that component. So the factorization of this component is none other than x minus 1 and x plus 2. Now that is meaningful, and this component is now the combination of both of these conjugate terms and yet this conjugate in the denominator, that particular component is still intact. So you need to pass it to the next line. Now all you need to do is to simplify. Do you need to wait until one more line to see the cancellation? Or if you can see it right away, what you see here is x minus 1. X minus 1 cancels it x minus 1. And then once you have it, do the simplification right away, plug in 1 over, you're going to get 1 plus 2, that's going to be 3. And then within the square root, you're going to get again 1 plus 3, it's going to be 4. Square root of 4 is going to be 2, so 2 plus 2. Simplify it. Even if you leave a simplification, in most cases, in 99% of the cases, in mathematics, it will recognize the answer. By any chance, now, for instance, if this is an answer that you're trying to input, if you put it correctly in this form, mathematics should recognize it. But by any chance, if there is a mismatch, and if you believe that you had the correct answer in an assignment, and if mathematics marked it incorrect, that's exactly when you should alarm me, right? You should get my attention, and you can earn some credit on those problems. Sometimes, in most cases, it could be the complete credit. So that's where you need to save your work. You should be able to show your work in order to get the credit. So in this scenario, when you simplify, you're going to get 1/12 if you simplify further. All right. So now this bonus example is nothing uh, significant, and it will lead, of course, it is not significant in terms of the computation, but it looks pretty intimidating once you look at it. But once you start computing it, you will feel it has nothing. It is just the same similar thing that you've been taking. So let's try to read and try to work it out. And soon you will see these kind of problems, especially this term that you see here. The form of this kind of a limiting problem has a significance, a continued significance in our conversation. Now, the first thing, we need to do this computation. That's what you need to do. This on this definition. Now, the definition is this. F of x is given right here. And don't forget, here you need to have f at 1. So you need to compute f at 1. So in other words, just plug x equals 1 in this expression, and then let's try to simplify. When you plug it in, what do you get? You're going to get like 2 minus 3 plus 1. So in fact, it's going to be, oh, it's nice. It's going to be 0. Not all cases would give you just this kind of a scenario, but in this case, it works out perfectly. And now let's do this. Limit as x goes to 1, you do have f of x 2x squared minus 3x plus 1 minus, right? So this is nothing other than f of x. And this term is none other than just 0. The whole thing is divided by x minus 1. Now, all you need to do is to simplify this term. 2x squared minus 3x plus 1 divided by x minus 1. Now, you know what to do in this kind of scenario. It's none other than a factorization problem. So let's factorize. Let me give you a trick in this kind of a situation. When you plug in x equals 1 in this expression, and when you see it's going to be 0, that simply means it has this hidden factor. which is x minus 1, which is known to be the bad factor when x goes to 1, right? When x goes to 1, x minus 1 is going to be the bad factor, taking both the numerator and the denominator to 0. So this is what I'm going to do. I'm going to write that factor right away. Let me just write it in front. The purpose is to have this factorization. In the denominator, I already have x minus 1. Now the mystery is this second factor. It's pretty easy to recognize. All you need to do is to figure out the first and the last components, and the rest, the middle term, will work out, balance out like perfectly. So what you're going to do is, first of all, you're going to write like, you need to have 2x square, but you already have x here, so you're going to put 2x right there. And then you need to have plus 1 at the end, but you have minus 1 here, therefore you're going to put minus 1. Now look at this. When you combine the first two terms, you're going to get 2x square. When you combine these two terms, you're going to get plus 1. So the first term and the last term would work out well. Now the question that you should really ask is, do we get this? If you do this perfectly, it's going to work, because x minus 1 is in fact a factor of this term. So how are we going to make sure? Let's work with this. This one, the middle terms, right? When you multiply this, you're going to get minus 2x. And then when you multiply these two terms, you're going to get minus x. So minus 2x minus x, it's going to be minus 3x. That balances perfectly. So with that, here we can cancel the bad factor. And once we do that, in the denominator, don't forget we have 1. It's not 0, right? So now plug in x equals 1 right here. So you're going to get 2 times 1 minus 1 divided by 1. So it's going to be 1.